Good day, class. Welcome to the notes on adding and subtracting vectors. So write down the title for the notes for today. Um, Notes on adding and subtracting vectors. Adding and subtracting vectors. Okay? Write this down. The main method we're going to be using today to add and subtract vectors is the parallelogram method. We'll go into that in a minute. But before we start, let's write down the learning objective for today's lesson. Learning objective. Alright, write this down. By completing 80% of graded classwork problems, you will apply the parallelogram rule in adding and subtracting vectors. Okay? Adding and subtracting vectors. When you're done using this rule, you see that your final answer looks just like a parallelogram. So this is the learning objective for today. Alright? The classwork I'll give you will be in a packet, and a completion of 80% of that will mean that you've met the objectives for today. So why is this important? Where is this used in the real world application? Write this down. The application of this is in auto design. And the people that do this are automotive engineers. Automotive engineers. Automotive engineers make anywhere between 55 to $75,000 a year. Okay, that's how much salary they receive. Just in case that's what you want to go into. So how do automotive engineers use vectors? Well, vectors are used to calculate the amount of drag. Let me move this up a little bit. The amount of drag that air exerts on auto models before they are produced. Alright? We know that cars do not drive in a vacuum, they drive in an atmosphere with a lot of air. So if a car has a lot of air drag, then it's going to waste a lot of gas. If it's very aerodynamic, little air drag is going to save a lot of gas. So that's why it's important to calculate the air drag on a car before it's designed, so you can make sure it's fuel efficient. Now let's take a look at some definitions and components of vectors. Okay? Write this down. Definition. We're going to define a vector. A vector is a quantity that has magnitude and direction. It has magnitude and direction. Okay, it has two critical components. It has a magnitude, which is size, and it also has direction. Geometrically, a vector is represented by a directed line segment. Okay, directed line segment. This you learned in geometry as array. Okay, also known, you can also call it array. Directed line segment. All right. So what does that look like? What does a directed line segment look like? Let's create a vector from the blue. Let's create a vector. Let's call it vector p. Okay, vector p. So it looks something like this. So there goes vector p. All right. So that is a line segment with a direction. So there goes your vector. All right. So some important parts to know about this vector is where the tail is and where the tip is. Okay, the tail is where you start from. So whenever you want to identify the tail of the vector, you can put a coordinate system here, right here. That is your origin or your 0, 0. Okay, that's basically where your origin is. Okay, so wherever you're starting from, that is the tail of the vector. All right, that's the tail of the vector, and this right here is the tip of the vector. This vector can move all over the place, but the length and the direction always stays the same relative to this coordinate system that we have here. Okay, so tail, don't forget, tail is where you start from, the starting point, and the tip is the terminal point. All right, so if this is 0, 0, this is 0, then can I represent this vector using coordinates? Definitely I can. So this is how you do it. You have an x component and you have a y component. All right. So to find the x component, I just count 1, 2, 3, 4, 5, 6, 7, 8, 9. So I went 9 units to the right? So I put a 9 for the x component, and then for the y component, I just go 1, 2, 3, 4, 5, 5. Okay. If you don't have graph paper, that's fine. We're going to be using graph paper in a minute. So that is this uh, coordinate representation of the vector just means I'm going 9 units to the right and 5 units up, starting from the tail or the origin 0, 0. Okay, so this is another way that you can represent vectors. And the length of this vector that can be found using Pythagorean theorem is the magnitude. All right, we're not going to do that today. All we're going to be focusing on is how to manipulate these coordinates. All right. So let's write down some more information. The length of the vector is the magnitude. It's the magnitude. All right. And the arrowhead, which is also known as a tip, um, indicates the direction. Okay. That indicates the direction. All right. Okay. Let's take a look at some examples having considered these definition and components. Let's take a look at example number 1. So bring out your worksheet. Oh, forgot. Oh, let's talk about some applications of vectors first before we do some examples. So this is an example of a vector uh, that's being represented by an organ of the body, the human heart. Right? The human heart has diastolic and systolic phases, and those phases creates vectors in the heart, and that's what causes blood to flow. So when you have your diastolic phase and the ventricles relax, these vectors indicate that blood is coming into the heart. These arrows indicate blood flow into the heart. and then during the systolic phase when the ventricles contract, see these arrows right there indicate that blood is going out of the heart. Okay, so this is one biological or anatomical application of vectors, which is in the human heart. Okay, so you see all these arrows here represent vectors. The vectors in this case is blood flow. Okay, now I'm going to challenge you with this. Think, write, share. All right, now let's take a look at some examples. Looking into your worksheet, let's try number one. Number one says, where to find resultant vectors using the parallelogram method. We're just going to use the parallelogram method today. We don't have to bother with the triangle method. So just using the parallelogram method. So using the parallelogram method, do you notice I gave it a name? The name of the parallelogram method is also known as the tail-to-tail method. Okay, so we're going to put the tail of two vectors together and see if we can find the resultant or the sum by using the parallelogram method. Okay? Now, to find this, we need to determine the coordinates of these vectors so we can move them all around the place. Alright, so vector P, what are the coordinates of vector P? We need to start, this is the origin right here, 0, 0, you can put your coordinate system over there. That's for vector P. And what are coordinates? For that one, we're going to start there, and then we're going to start counting. Okay? Let me make the tip of my pen a little bit smaller so that it fits. Line style. Okay, let's that one. Alright, so to count for vector P, you start from 0. This is 0 for vector P. This line right here is 0 for Q. This is 0 for R. And this is 0 for S. Why am I putting zeros there? That is the tail. The tail is a 0. That's the tip. That's the tail. That's the tip. Tail, tip. Tail, tip. Okay? Alright, and this is my coordinate system, my X and my Y coordinates. So if I want to do this, I start from the tail. I go 1, 2, 3. That's 3 on the X. And then 1, 2, 3, 4, 5, 6. 6 on the Y. Okay, this means starting from the tail, you're going to go 3 units to the right, 6 units up to end up at the tip of this vector right here. That's vector Q. How about vector Q? Vector Q, same story. Starting from the tail, you go 1, 2, 3, 3 to the right, 1 up, 1. Remember, this is an X. X comes first, and then Y comes second, okay? So you have to keep that order in mind. Now, let's just bring this in. Let's do vector R. So for vector R, starting from here, go 1, 2, 3, 4, 5, 6, 7. For vector R, we're going to have 7 to the right and then 1 up. So that's R. And let's not forget S. S we're going to have starting from 0. 1, 2, 3, 4. We're going to the left because the tip is to the left, right? 1, 2, 3, 4. Since we went to the left, what direction does that indicate on the x-axis? Negative, yes? Negative 4, right? 1, 2, 3, 4. Negative, positive. Going down, 1, 2. Starting from here, 1, 2, 3, 4, and you go down 1, 2. So that's negative 2 for the y component of this vector. Right? So we all have our vector written as numbers. So with these numbers, we can easily move them all around the place. So now we're going to do vector P plus R. So what we're going to do is we're going to take vector P and R, place their tails together on the same spot. Since vector P is in quadrant 1 and vector R is in quadrant 1, the whole region is going to be just quadrant 1. So we're going to make quadrant 1 a really big quadrant in our coordinate system. So let's draw our y-axis to the left as much as possible. in our x-axis to the bottom as much as possible, because I'm trying to make quadrant 1 pretty big, right? Because this is in 1 and this is in 1, so everything, the action is in 1. So let's draw vector P first. How do you draw vector P? To draw vector P, uses numbers 3 to the right, 6 up, starting from 0, because this is where the tail is located. So starting from 0, I'm going to go 3 to the right, 1, 2, 3, and 6 up. 1, 2, 3, 4, 5, 6. That goes vector P. Please, please, please use a ruler, or else your graphs will be inaccurate, alright? Make sure you have your ruler nicely aligned, and then draw vector P, alright? How did we get that again? We started from 0, 0. We went 3 units to the right, and 6 units up. That takes me to vector P, okay? My points have to be very fine here, or else I might ruin the answer. Alright, so how about vector, this is vector P, put the name right by it, P. And then we now have to draw vector R. Alright, so vector R, we're going to go 7 units to the right and 1 unit up. Alright, 7 units to the right and 1 unit up. Let me make my pencil tip a little bit thinner so I can be accurate. So 1, 2, 3, 4, 5, 6, 7 units to the right, 1 unit up. Boom. There goes the tip of vector R. Alright, so you draw your line segment from here to there. Alright, so there you have P, and here you have vector R. Okay, vector R. It's a pirate vector. Anyway, so let's find the sum. So how do you find the sum? What you do is you copy one of the vectors. Okay, you either copy the P or you copy the R, and then you create a parallelogram from there. So which one should we copy, P or R? Let's copy R. Okay, I'm going to copy R right on top of P. Okay, so R is 7 to the right and up 1. So starting from the tip of P, I'm going to do R again. Okay, so be careful, watch this carefully. I'm going to go 7 to the right, 1, 2, 3, 4, 5, 6, 7, and 1 unit up. There goes the tip. Alright, 7 to the right, 1 unit up. Now this component I'm drawing here must be drawn with a dotted line because it's not actually R. It's the movement of R, so this has to be dotted right here, like that. Okay? That is R copied over here. Now we're going to create a parallelogram by connecting these two dots right here. This dot and that dot will be connected like that. Alright? Now, this is a mistake most people make. They think they're done. No, you're not. The final answer is a diagonal by connecting the two tails to these two tips you have here. So these two tails to the two tips here. Okay? So, two tails, so that's where you start, to the two tips right here. Alright, let me do that again, because I think I'm a little bit off. So, two tails to the tip right here. That is your answer, okay? So you can make a line extension and call that P plus R, vector P plus R, okay? So what are the coordinates of vector P plus R? Well, you can figure it out. Let's count. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the right. And how many up? 1, 2, 3, 4, 5, 6, 7. 7 up. Okay, this is my geometric result. Am I right or am I wrong? How can I tell? Can I verify using a different method that this answer is accurate? Yeah, that's what the numerical verification component is for. We can actually tell if our answers are right or wrong, which is really cool. A cool thing about vectors. Okay, so let's do it numerically and see if our answers are right or wrong. So for vector, we're going to do vector P plus R, right? So vector P is 3, 6. Vector R is 7, 1. So we need P plus R. P plus R. So how do we compute that? We just add in, right? You just simply add these two vectors. So when you add in these vectors, you just add in downwards, and you're going to get 10, comma 7. Is that what we have here? Yes. So our answer checks out. Alright, so you're not confident you got this. Alright, now let's take a look at another example. It's going to be slightly more challenging because you're actually going to be scaling one of the components by a scalar multiple, which makes it somewhat longer, right? And then you compute the difference. Alright, moving along, let's take a look at number 2 on your worksheet. Number 2 on your worksheet. Right here. So, for this one, we're going to try and figure out 2q minus p. 2q minus p. So, let's write down what 2q and negative p look like, and then I'll give you guys a chance to try out the problem, 3 minutes, and then I'll go over it with you, okay? So, we know that q, vector q, vector q before is, if I look here, vector q is 1, 2, 3, 3, comma 1, right? And vector p is 1, 2, 3, 3, comma 1, 2, 3, 4, 5, 6, 3, comma 6. All right, 3, 1, 3, 6. Yeah, that's what we had before. Okay, so what does 2q look like? If this is q, then 2q has to be what you get by doubling the vector components. So simply 2 times this, both of them, right? 2 times 3, which is 6. And then 2 times 1, which is 2. So you basically multiply this by 2 and multiply that by 2. That's what 2q is. Since we're doing negative p, guess what? We're going to multiply p by negative p. So what does negative p look like? That's what it looks like. You simply distribute negative to these two numbers right here, okay? So you make this negative 3 and negative 6. So that goes 2q and that goes minus p, alright? So I'll give you 3 minutes to try and see if you can do this too using the parallelogram method, and then I'll show you the answers. Alright, welcome back. Let's do this. So first thing I want to do, let's look at the quadrants. Where are the quadrants at? 2q is in the first quadrant, and p is in the first quadrant, so negative p is going to be downwards here. It's going to be the opposite of this. So this is in quadrant 1, this is going to be the opposite quadrant, which is quadrant 3. Okay, so we're just going to place our coordinate system right in the center so that they both fit. Okay, just put it right in the center. Alright, so there goes my coordinate system right here. Alright, so let's draw 2q first. Okay, know that this is 0. So to draw 2q, I'm going to go 6 to the right. 1, 2, 3, 4, 5, 6. And 2 up. 1, 2. Boom. Okay? 6 to the right, 2 up. As indicated here. Put your vector. Remember the tail starts from here. And the tip. And ends at the tip right there. Okay? So label your vector. This is 2q. Now how about vector p? Negative p. That one you go 3 to the left. 1, 2, 3, and down 6. 1, 2, 3, 4, 5, 6. Oh, that was close. 6. Alright? So now, let's draw the vector. So you draw your vector like this. Okay? So now you're going to copy one of them. You're either going to copy 2q or negative p. Alright, let's put negative p here so we don't forget. So which one do you want to copy? You could copy this, or you could copy negative p. Let us copy 2q, okay? So we're going to paste 2q on the tip of vector p. So we're going to go 6 to the right, 2 up. So let's do that. 1, 2, 3, 4, 5, 6 to the right, and 1, 2. I lost track. Let me do that again. 1, 2, 3, 4, 5, 6, and 1, 2 up. Alright? See the direction of 2q going up? That is exactly how the direction here should be, but you must use a dotted line because that's not actually 2q. It's just the movement of 2q, projection of 2q on the tip of negative p. Alright? Pointing in exactly the same direction as 2q. And then p, you don't even need to do any work for p, you know it's going down, right? So you simply move it this way. Are we done? Absolutely not. You're done when you draw the resultant vector, the sum, right? So you go from the two tails to the two tips. These are the two tips, these are the two tails. So it goes from here to here. Boom. There goes your answer. Okay? And then you can label your answer. This answer right here is 2q minus p. Alright? What are the coordinates of 2q minus p based on our graphical result? Let's see, it's 1, 2, 3 to the right, comma, let's do that again, 1, 2, 3 to the right, and go down 1, 2, 3, 4, negative 4. 3, comma, negative 4. That's our graphical result. Is that right? Well, I have no idea. I have to verify numerically. If my numerical result is the same as this, then we'll celebrate that I'm correct. Okay, so let's do the numerical analysis. So we have 2q. As a consequence of distribution of 2 to these two, we came up with 6, comma 2. And then negative p. As a result of distributing negative to the p components, we have negative 3, negative 6. Since we have already distributed the minus, we just combine them downwards, right? Because subtracting is adding the opposite. So we're adding the opposite of p, which is this. So just combine them downwards. Your answer is 3 plus 6 minus 2 is 3. 2 minus 6, negative 4. Excellent. That is exactly what we want. Okay? So thanks guys for listening to this presentation. Remember, it's going to be available online. You can review this notes at home, okay? Now we're going to get started on the classwork for today.